Hello everyone and welcome to the theory prep video on polynomial time reductions. So we did some reductions in the last video, so let's review. In the last video we said the problem solving halt reduces to solving halt on zero, by which we meant that if we could solve halt on zero, then we could also solve halt. So intuitively this sort of gives us a way of comparing the difficulty of problems, right? Because basically we know that halt is no harder than halt on zero because, well, if we can solve halt on zero, we can also solve halt. So sort of like halt is an easier problem than halt on zero. More specifically, we'll be careful to say that halt is weakly easier. When we say weakly easier, it means it could be easier or it could be just as, it could be equivalent in difficulty. But it's certainly not harder than halt on zero, right? Because if we could solve halt on zero, we could solve halt. So that sort of matches up with our intuition there. And so this actually lets us sort of compare the difficulty of problems, which is really interesting because functions are sort of these like nebulous abstract things. So we don't immediately have some way of comparing, oh, these functions are harder or easier to compute than these other functions, but reductions let us do that. Because if f reduces to g, then f is weakly easier than g. So that allows us to compare the difficulty of f and g, right? Because if f reduces to g, then using g we can solve f. So g's no harder, or then f is no harder than doing g. So in theoretical CS, we're often interested in what problems are sort of similar levels of difficulty or different levels of difficulty, like which problems are easier, which problems are harder, and so reductions are really useful there because they let us compare how hard problems are. And in 121. We're usually only concerned about polynomial time, like, n to the 5th, n to the 10th, like those are all the same thing. It doesn't really matter to us. In 124, we'll actually care about sort of more granular differences in runtime, but 121 is really theoretical in its approach there. And so basically what we want to show with a reduction, in the last video we were just showing like, if you can solve this thing, you can solve this other thing, but with polynomial time reductions, we want to show that if we can solve g, then we can solve f with only sort of polynomial time overhead, with only an additional polynomial amount of runtime, because that will allow us to sort of say like, oh, if we can solve g, then we can sort of efficiently solve f. Great. So now, we're going to add in polynomial time to our reductions. So let's say f and g are two functions, right? They can be any function we want. So we'll say f reduces to g, denoted by f less than or equal to g. And the reason we use this like less than or equal to with a little p here is because, well, if f reduces to g, right, if suppose we have g, then we can compute f. Well, then that means like f is like weakly easier than g. So we say f reduces to g if there's a polynomial time computable r, such that for every input, if we input that to r and then run g on it, we can solve f with it, right? So this says basically if we had some solver for g, well, then first we could run some, like r is polynomially time computable, so we might have some program pr that computes r. So we first run pr on it, and then if we could compute g with some program pg, then we could just run pg on that. So it says that we can compute f as long as we can compute g with really only a little bit more time. And this is important because it allows us to say like, oh, this problem is about as easy as this other problem. So we're going to spend the rest of this time doing a reduction, and we'll reduce 3-set to i-set. And let's talk about what these problems are first. So in the 3-set problem, we're given some formula containing binary variables, which we'll label x1 through xm. And the formula is composed of a bunch of like binary formulas. So it's composed of the and of a bunch of clauses. So each of these are clauses, and each clause has 3 variables or their negations, with the negation being denoted by a bar over the variable, joined by or together. So down here we have like this first clause is x1 or x2 or not x4, and it must be true that not x2 or not x3 or x3 is true, right? So it's basically a bunch of clauses, and each clause, at least one thing must be true, and then all of the clauses have to be true. And we call this a 3CNF, which stands for 3 conjunctive normal form, conjunctive because it's the conjunction of a bunch of clauses of ors, and normal because normal just means sort of like a standard form. Like there's many different ways to write this, but this is just a standard way of doing it. And so given this function, 3set asks if there's some assignment of xi's satisfying this equation. So that's one interesting mathematical problem. Another that seems completely unrelated is the problem of iset, or independent set. So we're given some undirected graph, G with some vertices and some edges, and some number K, and our goal is to see if there is a subset of at least K of the vertices such that that group of vertices is an independent set. And an independent set is something where there are no edges between members of S. In other words, there are no neighbors. They're all independent from each other. So mathematically, we say for any S and S prime, they're not equal to each other in this set, like the edge between S and S prime is non-existent. And at first glance, these problems seem just super unrelated. One of them is about binary formulas, Boolean algebra, and one of them is about graph theory. But actually, we'll see that we can reduce 3set to iset. In other words, if we have some solver for iset, then we can solve 3set as well. So you're already seeing sort of the power of reductions. They allow us to reason about sort of the difficulty of problems that are completely different, and it allows us to also use one type of problem that really seems completely different from another problem to actually solve the other problem. So now let's discuss how to do the actual steps of a reduction. So if we go back to our definition, remember that we need to show that there exists some polynomially time computable R, and then that applying that and then G gives us F. So contextualizing in our example, we would want some R such that we apply R to a 3CNF, and then we get some graph, and then we apply the iset solver to that graph, and then we get the correct answer for our 3-set problem. And so the first step then is to define the reduction R, to define this transformation. And this often requires some trial and error to discover how the problems are similar, what sorts of structures we could convert back and forth. And then the second step is to prove that R runs in polynomial time, because that's part of the definition. The last step is to prove that f of x equals g of R of x for any x. And since these are both usually binary functions, both f and g are, this is usually equivalent to proving f of x equals 1 if and only if g of R of x equals 1. And as we learned in previous weeks, we can therefore prove the forward direction. So we could prove like f of x equals 1 implies that g of R of x equals 1. And then we could prove the backwards direction, that g of R of x equals 1 implies f of x equals 1. And instead of some of these, we could also prove like contrapositives, right? Like in this case, the contrapositive would be f of x equals 0 implies g of R of x equals 0. And sometimes which one to prove will just sort of depend on the structure of the problem. So it's good to be able to sort of rephrase these so that you can make your proofs as easy as possible for yourself. So let's go back to our problem. Remember, we're trying to reduce 3sat to iset. So we're trying to find some way to use an iset solver to solve 3sat. So in this case, we're taking in some 3CNF, right? And we need to use some algorithm that finds independent sets to find a solution to the 3CNF. So first, we might think to make like the literals like x1, or starts with x0, x1, all into like vertices. And we'll also make the negations into vertices, like x0, x1, right? That would be a good idea, just to start turning it into a graph. And then it's probably a good idea to connect each literal to its negation, because we're going to get back an independent set, and we don't want like x0 and not x0 to be in our independent set, because we'll probably try and use that to set the binary values. And if x0 is in the independent set, then we'll probably set x0 to 1. And if the negation of x0 is in the independent set, that might imply that we should set to 0. So we don't want to have both of those be in the independent set, because then we might not really be sure what to do. And then also, if we have some formula, if like one of the clauses is like not x0, or not x1, or x3, then maybe it would be a good idea to connect those vertices as well. That way we can make sure like our independent set sort of has to contain things in all the different clauses, so we have a better shot at sort of satisfying all of them. And obviously this isn't like a proof or anything, but this is maybe some ideas and thoughts about what to build. So if I was just like doing this reduction, I didn't know how to do it, this is sort of this types of stuff that I might start with. And then eventually I might get to something where I feel like, oh, this is a polynomial time reduction, and also I think that this will work. So playing around with that is a really important part of doing the reductions. All right, let's now go through the proof. So again, the first step is to give the reduction. So let's say we have some 3C and F. So first we're going to number the clauses 1 through M, and I've given an example 3C and F below. So the clauses, this will be clause 1, this will be clause 2, this will be clause 3, and for each of the clauses, so for the ith clause, we're going to create nodes where the name of each node will be like the number of the clause and then the literal. So for example, for this first clause here, I'll have one node 1 comma x0, and then I'll have one node 1 comma x1 bar, and then I'll have one node 1 comma x2. And then I'm going to connect each of these into a little triangle. We'll call this like the clause 1 triangle. And then I do a similar thing for 2. So 2 comma not x0, 2 comma x1, and 2 comma not x2. And I'm going to connect these. And then now, for every one of these nodes, for any node like I, y, I'm also going to connect it with the node j, y bar. So if there's any node, for example, this node has x0 or not x0, right? So for any node with its negation, so for example, this has just normal x0, I'm going to connect those. Another example is here. This is not x2, this is x2, so I'm going to connect those. So basically, the second part of the tuple represents like the literal, and so I'm going to connect any literals to their negations. Finally, we'll also connect x1 and not x1 here. And then we'll also make a triangle for the last thing. So we'll have x1, node 3 and x1, then we'll have 3 and not x3, and then we'll have 3 and x2. And again, we'll connect all three of these things. And now we'll connect this x1 clause to this not x1 clause, and we'll connect this x2 clause to this not x2 clause. And there's no like x3 clauses, so that's going to be the reduction that we're going to be doing. And here's where we can sort of abuse. Remember, we said we only care about polynomial time. We don't care about like n to the third, n to the fifth. So we can be really lazy about how we construct this reduction. So you could just be like, well, there will be, if m is the number of clauses, there will be like 3m nodes. So you could construct like a 3m by 3m adjacency matrix. Then for each row, you could add the edges that would correspond to the clause triangle. And then you could also add the edges. You could scan through the entire 3C and F to look for any like negations of that literal, and then also connect those edges as well. And this would be like super inefficient, right? It'd be like, huge coefficient on m squared, but it would certainly be polynomial time. And so the runtime analysis is not really the focus of 121. We're more concerned about sort of the structures of problems, and so that's why we let you sort of do any sort of polynomial analysis is perfectly fine here. Great. So now, remember, the next step is to prove that f of x equals g of r of x, or in other words, we're going to prove both directions of f of x equals 1 and if and only if g of r of x equals 1. So first, we'll prove the forwards direction. So we want to prove that if, like, this formula is 3 satisfiable, then the transformation we can find an I set in, right? So here, I've drawn this same formula that we had, and then I also drew the, this is from the textbook, I copied in the graph that would result from the transformation or the reduction. So suppose we have some satisfactory assignment for the 3C and F, right? So we have some x, right? And in this case, while I walk through this, I'm going to give a concrete example just because I think it will help understand like what exactly are we doing here. So here's a concrete x that satisfies this. This first clause is satisfied because x0 is satisfied. Second one is satisfied because x1 is satisfied. Third one is satisfied because x2 is satisfied. Great. So for each clause, we know that at least one literal must be true, right? So again, that would be x0 here. So now we're going to take the vertex in the graph that corresponds to that literal. So here it's this vertex, and we're going to, I'll use a different color, we're going to put that in the I set. So here we'll take the one corresponding to x1, and there we're going to take the one corresponding to x2, and we'll put that in. And I claim that this is going to form an independent set. So we'll call this set S. And now, how do we know that this is an I set? Well, we have to check that there are no edges between these things, right? And there's only two types of edges because we constructed this graph. First, there's the edges between a literal and its negation, right? Like, for example, these are in red here, right? Between like x1 equals 1 and x1 equals 0, right? And we know that these cannot be in our independent set because we picked the vertices in S based on some assignment here, right? And so there's no way that some x could lead to like both x1 and x1 bar being true because x1 is either 0 or 1 in this assignment. So it's not possible for those edges to be in the independent set. Second, the other type of edges that we added, which are in black here, are between two members of the same clause. But remember, the way we constructed S was by going through each clause and taking exactly one vertex in each clause. So since there's one vertex from each clause, there's no edges between elements of the same clause as well. So this is an independent set. So that's the proof of the forwards direction. So now let's do the backwards direction. In particular, we're proving if g of r of x equals 1, so if there is an independent set in the transformed graph, then f of x equals 1. So there's a satisfying assignment for the original 3CNF. So again, what we're going to use is, well, since there exists some independent set, we're going to take that independent set and we're going to use that to derive some x that satisfies the 3CNF. So again, below I've put the equation, which is the same one that we've been working with as an example, and we're just going to select an independent set here. So I'm going to take x0 equals 1, this node, and take x1 equals 1. We'll do it in red again, so it's easier to see. And then we'll also take x3 equals 0. And this is clearly an independent set. There are no edges between these three nodes, and it's of size 3. So, great. So now, for every vertex in S, so we assume that we have some independent set, right? Because g of r of x equals 1. So we can assume we have some independent set S. We'll look at each node. And if it's of the form kxi, then we will set xi equal to 1, where xi is, right, like the x is going to be our thing that we put into our 3CNF to satisfy it. And we're building that up here. And otherwise, if that node is of the form like k not xi, then we'll set xi equal to 0. And at the end of the process, there might be some xi remaining, so we'll just set them to 1. So again, it's helpful to have a concrete example here, so let's go through this. So first, we'll look at this vertex. This is x0 equals 1, so we'll set x0 equal to 1. Then we'll look at this vertex, x1 equals 1, so we'll set x1 equal to 1. Then we'll look at this vertex, which is x3 equals 0, or in other words, not x3. And so we'll set x3 equal to 0. And we had nothing to set x2 to because we never encountered it, so we'll just set that to 1 by default. So that will give us an equation. And actually, this gives us exactly the equation that we previously had, so we know that this will work as a satisfying assignment. But I think the concreteness helps you understand, like, oh, what exactly are all of these steps doing? So first, you might ask, well, this step 1 and step 2, like if there are certain vertices in S, then you might have a conflict. Like you might have to set xi to 1 and xi to 0. So let's make sure that this doesn't happen. This is called well-definedness. It means like if you have a bunch of different rules or different ways of defining things, they come out to the same thing. So we know this can't be true because if somehow both 1 and 2 were both invoked for some xi, this would mean that the set S has to contain some vertex like kxi and some vertex k prime not xi, right? Because in order for 1 and 2 to be invoked, both of those vertices have to be in there. And that violates the independent set property, because remember when we constructed this graph here, we drew red edges between any nodes representing a vertex or any nodes representing a literal and its negation. So that means that we can't have that. So this will be well defined. In other words, we won't, through this procedure, we won't have to set like x to both 0 and 1 in some place. So great. So now we have to show that whatever x we get actually is a satisfying assignment. So the first thing that we're going to argue is that we know that the size of the independent set is M. Technically, the independent set problem only asks us to find an independent set of at least size M, but we can always reduce that to an independent set of size M by just taking away points, because taking away points obviously won't cause any like new neighbors to appear. And so the first thing that we notice, so in this case, M is 3, right, in our example below. So S can have at most one vertex in each clause triangle. And by clause triangle, I mean like something like this, right, where it's one of these triangles that we created from an initial clause. And we know that S can only have one element in each of those because all the elements of that triangle are connected, and S is an independent set. So therefore, S must have exactly one vertex in each clause triangle because there are only M clauses, right? So for example, if like if S didn't have a vertex in this first clause triangle, then it would have to have multiple vertices in one of these two clause triangles, which we know isn't possible, right? Because it has to have at least 3 vertices, and that can't happen because everything in those triangles is connected. So that means that S must have exactly one vertex in each clause triangle. So by our definition of X, remember this procedure that we defined above, we selected Xi's such that the literal corresponding to each vertex in the set S is true, right? So each vertex in the independent set, and we know there's exactly one vertex in each clause, will be true. And that means that based on the way we define this graph, each of these triangles corresponds to a clause in the initial graph, and the way we defined our X was by making sure that one vertex, or in other words, one variable in each clause was true. And that means, well, then that's 3C and F must evaluate to true, right? Because for the first clause, well, as we just showed, there must be some vertex in the independent set that's in that clause. And then we know that our procedure made us set X such that that literal would evaluate to true. So this first one evaluates to true. To be concrete about this, we were forced by this vertex to set X0 equal to 1. That means this will be 1, so this first clause checks out. We were forced by the clause by the vertex in the second clause to set X1 equal to 1, and so this will check out. And then we were set by the clause in the vertex in the last clause to set X3 equal to 0. So this will be true, which means that this will also check out. And so you can see that hopefully that concrete example helps you understand what the proof is saying. But now we've proven both directions, right? So we've proven that f of x equals g of r of x, and that's exactly what we want to prove, and that completes our proof. And this is really interesting because basically what we've proven is if we get some 3C and f in polynomial time, we can convert that into some graph and then use a solver for the I-set problem to just solve the original problem. So solving 3-set is as easy as solving I-set. If we knew how to solve I-set, we would also know how to solve 3-set. And that allows us to have a comparison between two problems that really seemed very different at first.